if this is R, I can write the inverse relation R inverse just by flipping the coordinates. It's going to be y1, x1, y2, x2, y3, x2, y1, x4. I can always do this. I can always just exchange the x and y coordinates, make the first element the second, and vice versa, and get an inverse relation. But this inverse relation isn't always a function. Okay? This one is not going to be a function. And why is it not going to be a function? Well, first of all, I can see that it didn't send, and maybe I should do this in the same way I did over there with the purple. It didn't send y4, y5, or y6 anywhere. And how do I know that? I know that without even having to look at the inverse relation that I've written here. I know that because the original function didn't map anything to those points. It missed those. It didn't hit those. It didn't send anyone there. That was fine. It didn't have to do that to be a function, right? It had to send every element of the domain somewhere. It didn't have to send something to every element of the range, or every element of the codomain. We're going to talk about ranges in just a second, because the range is the set of all the outputs. So the range of this function would be y1, y2, y3. The point is, its range doesn't have to be the entire codomain. But if it isn't, and I've kind of blown the surprise on myself here, but if it isn't, then the thing is not going to be invertible, because the elements that of the codomain that it misses, that it doesn't map anything to, aren't going to get sent back to anything. So the inverse relation is not going to be a very good travel agency, because it doesn't send these people anywhere. Although this is where the analogy kind of breaks down, because travel agencies send people to countries, not. But the point is, it's not going to send the things that didn't get mapped to. It's not going to map them to anything, so it won't be a function. The other reason it's not the inverse is not a function is because, and you might have noticed this already, y1 got sent to two different places. It got sent to x1 and to x4. And how did I know that was going to happen? I didn't have to look and check, right? Well, it got mapped to by x1 and x4. The function f, or this relation, I'm looking at the diagram, I have to be careful. This relation R inverse, or this relation R, it mapped x1 and x4 to y1, so R inverse is going to map y1 back to x1 and x4, right? Inverting a function, the inverse function, it sends everything back where it came from. Inverting it just sends the stuff back where it came from. So if the function, and this is the second property that functions have to be invertible, if the function sends two or more things to one place, the inverse function, the inverse relation, is not going to be a function, because it sends that thing or things back to two or more different places. So these are the two ways that a function can fail to be invertible, is by not hitting everything, by not mapping to the entire codomain, the range of the function being the set of outputs, not being the entire codomain, means that the inverse is not going to be a function because it doesn't map everything somewhere. I think that's called being total. And if the function, if it maps two things to the same place, two or more things to the same place, even though that's okay, it's still a function. Its inverse is going to, the inverse relation is going to map that thing or things back to two or more places, and then it will not be a function. I think that's called being single valued. It will not be single valued. It will have elements that are multi-valued. Their value or output associated with them is multiple. They get sent to multiple things. So this is where we get these two concepts, which you might have heard of, being one-to-one and onto, or injective and surjective. The motivation for this is that we want conditions on functions that are going to let us tell when they are invertible. And if they don't have them, we can try to give it to them. We can try to make them invertible by restricting the domain and or codomain of the function. And so let's take a look down here. We have these as well. So first a function, we say a function is injective or one-to-one if for every x1 and x2 in the domain of f, if the outputs are the same, then the inputs are going to be the same. If f of x1 is equal to f of x2, then x1 is equal to x2. What does this mean? This means that it can't send different things to the same place, right? If what comes out is the same, what went in is the same, right? So we can't this function up here would fail that because I have f of x1 is equal to f of x4. These are equal to y1, but of course x1 is not equal to x4. Right? That's exactly what we're trying to get around with this. And this is the typically the trickier one to understand. But if it, again, and sort of think about this for a minute, let it sink in, but I find it helps if we note to ourselves that functions are single-valued. So the exactly one criterion, if for all x1 and x2 in the domain of f, x1 being equal to x2 implies that f of x1 is equal to f of x2. So here, if the inputs are the same, then the outputs have to be the same. The converse of this statement is that if the outputs are the same, the inputs have to be the same. And this is what we need for it to be injective or one-to-one, for it to be invertible, for it to be flip-aroundable. So in order to this condition of being single-valued, to make sure the function, the inverse, when you flip the x and the y's around, to make sure that inverse has this property in pink here, well, you flip around the property and make the function have that flipped-around property. If that helps you think of it, I find that can help students understand this a little bit better. It certainly makes logical sense. The second thing, the second condition, and so that again that corresponds to functions being single valued. But the second thing is this whole idea of the range or the set of outputs of the function being equal to the codomain, right? That it doesn't miss anything, and because it doesn't miss anything, the inverse won't miss anything or won't fail to send anything somewhere. It's going to be total. It's going to send everything in its domain somewhere if the function hit everything in the codomain. If its range, the set of all the outputs, was equal to the codomain, and this is being called surjective. This is called being surjective or onto, surjective or onto, and this is if the range is equal to the codomain, as we just said. And that formally, that means that for all y in the codomain, now it's y's because it's the target set, there is some x in the domain of f such that y is equal to f of x. So any element of the codomain that you can find, well, or that I give you, you can find me some element of the domain that gets mapped to it. Nothing does not get anything mapped to it, right? Everything in the codomain gets mapped to by something. And again, the sort of converse of this, right, is that a function is total, right, the every condition, if everything gets mapped to something. So if a function, this relation between the domain and the codomain, if everything gets mapped to by something, then when you invert it, flip it around, everything will get mapped to something. So again, converse conditions to guarantee that this condition, this criteria that functions have to meet, this condition that or this quality that functions have to have of being total, right? In order to guarantee that the inverse will have that, right? The flipped around version will have that. You flip around the condition and make sure that the function has that flipped around condition. Hopefully, as I say this, I'm doubting whether it makes it clearer or more confusing. If that helped, please run with that. Absolutely ponder upon that. If not, just ignore it and remember the definition. It's not so hard to remember. So okay, I think that is good for the conditions that they have to have being one-to-one and onto. Oh, and by the way, I should note to wrap this up, functions that are both injective or one-to-one and surjective onto are called bijective. They are bijections. So if you ever hear this phrase or see this phrase anywhere, that's what it means. Bijection. One-to-one and onto, injective and surjective, and these are the nice ones. These are the ones we like because these are invertible. Being bijective is precisely what it means for a function to be invertible. So I think that's a good place to leave it because I'm probably going to have to break this thing up already to get it to upload in a reasonable amount of time. And so in the next video, we will see this. This is what the conditions that we have to have for this is what a function is, what conditions it has to have to be invertible. In the next video, we will see if it doesn't meet these conditions, is there a way that we can make it meet these conditions? That will come at a cost, right? We're not just going to be able to do that for free. We're going to have to forget about part of the domain, and we're going to have to maybe forget about forget about part of the codomain. But in many cases, we can do that, and so we'll see how we do that in the next video.